In exercise 9I, we're going to look at what they call geometrical theorems about the parabola, and I guess they're calling it a geometrical theorem because it's focusing on angles. So we're going to be identifying particular angles and describing those angles in terms of the parameters associated with the parabola. Now, it is almost like the last things that you will learn about the parabola in terms of the parabola in its parametric form, and they are based on the properties that we've just established in the previous exercises. So what I've done, you might notice that I've introduced a page. I don't know if I can, whoops, sorry about that. What I wanted to show you was that I've also added another page, and I called it my summary, and it basically looks like this, where all I did was just wrote on a piece of paper what we've done so far. So I've started with the equation of the parabola, the parametric form for denoting the points. Some equations that we came across were equations for the chord in terms of the parameter. We know if a focal chord exists, then the product of the parameters is -1. That's not so much an equation. I'd say that's more like a property. We know that, and this is not an equation either, it's a property, that the gradient of the tangent is the same as the parameter at that particular point. This is an equation. The equation of the tangent, the straight line, can be written like that. We've also found that tangents intersect at this external point, which can be written in parametric form like that. The normal has a gradient -1 on P, and that again is not really an equation, it's a property, and the equation of the normal looks like that. Now, it's going to be these concepts that we're going to use to help us to explain the geometrical properties in this next exercise. So something about the angles that are created will be based on these properties that we've just learned about back in these other exercises. We saw that a tangent could be from what's that one? A tangent in Cartesian form, so XY form, the equation of a tangent would be written like that, the equation of a normal is written like that, and the chord of contact is written like in that format. Okay, let's go back to this 9I, these geometrical theorems. You know, really there are, I know I've written 3, 1, 2 and 3, but these two are so similar, it's almost like they're based on the one idea, and then, because they really only talk about one angle, then there is this angle that we're going to talk about in that third theorem. Okay. So geometrical theorems, like I said at the beginning, just means an angle created somewhere because we've got chords, tangents, directrix, a focal point, etc. Okay, so what is this particular theorem that we're going to learn about? It says if the tangents at either end of a chord are perpendicular, so the tangents end up being perpendicular, that is, they meet at 90, then the chord they pass through then the chord must pass through the focus. So the chord joins the tangents. So it's simply like this. You've got your parabola. You've got, what was it? If the tangent's at either end of a chord, so we've got our chord, we've got tangent 1, we've got tangent 2. If they meet at 90, now mine don't look like they do, but if we knew that was a 90 degree, then the chord must pass through the focus. So I guess if you're given if you're given information like this and they're talking about the tangents intersecting out here at 90 degrees, you know for some reason the chord that joins the points of contact of the tangents, that chord passes through the focus. Now, you could be already moving into the second one yourself. What do you know about a chord that passes through the focus? A chord that passes through the focus. If a chord passes through a focus, then it's called a focal chord. And if you've got a focal chord, then PQ is -1. Now, what's that got to do with this next situation? If PQ is -1, remember that this point of intersection of the tangents can be written like this. Now, if these two tangents are such that PQ is equal to -1, then our point of intersection is nothing special about the x, but very special about that. If my y value is -a of my point, where must the point be? If the y value of your point is this -a, you can see that these tangents intersect exactly on the directrix. So and that's what this says. If the tangents at either end of a chord meet on the directrix, the chord must pass through the focus. Or conversely, tangents drawn at the end of a focal chord will meet on the directrix. The tangents at the end of a focal chord meet on the directrix. And we could add more to that. The tangents drawn at the end of the focal chord meet on the directrix at right angles. There's both those features. So they intersect on the directrix and they make an angle of 90 degrees. Now in another video I'll take you through the proofs of those theorems. Not that generally you will be asked for the proofs of the theorems, but in seeing the proof you might see some techniques that you will use yourself later to answer particular questions. It is really important that you know these two theorems, and if you know, like I said, your features that you've just learned, your features of your parabola, then you won't have too much difficulty then relating those to the geometrical property, like, for example, the size of angles, etc. I think I should stop the video there and talk about the next geometrical theorem, the third one, in a different video. Just reinforcing that although they're called theorems 1 and 2, they're really just based on very similar properties.